Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, we will talk about a very interesting topic called curved bar nodes. This is Engineer Anas. I'm a structural engineer. English is not my native language, but I will do the best to make it clear as can as possible. In fact, curved bar nodes. This topic is very, very important, and this is a new topic in ACI code A 31819. If you open chapter 23, section 23.10, you will find here we have some provisions related to curved bar nodes. So we would like to understand what is the benefit from these provisions and how we can employ these provisions in our practice design. We will take also a very quick example to show how we can use these provisions in our practical design. These are the references that I have used to prepare this presentation. One of the common case that you will use the curved bar node provisions is the corbel. This is concrete corbel. Here we have the load, and this is strut and tie model to transfer the load from the corbel to the supporting column. Sometime you have nodes, same like this node, and this node, also this node. This node we are calling CTT. C mean one strut and two ties. And these here we have three struts and one tie, so we are calling this CCT because this node is attached with only one tie. One of the most critical things that we are facing when we are designing our structural elements using strut and tie model is how to satisfy the anchorage requirements at node. In fact, this is very, very important. So today we will talk about this area. Once you have two ties and strut, so how we can make sure that this area is safe against bearing and anchorage for the tension ties will be or will satisfy the code requirements as per ACI provisions. If you look for this corner, you can assume that this is corner in transfer beam or something similar like that. Here we have node. This node connects two ties and also one strut as shown. So this area is very, very crowded. So it's sometimes difficult to satisfy the anchorage requirement for the ties independently. So if you need to satisfy the ties anchorage in this direction, you have to make sure that from this point to this point, the length is enough to satisfy straight bar length or standard hook LDH length as per ACI code, and you have to satisfy also for the vertical reinforcement or the vertical tie. So ACI 31819 now provided some provisions that will help you to satisfy the anchorage requirement for this node using curved bar node to connect the two ties together, same like that, but we have to satisfy some requirements um, to make this node safe against the bearing failure. If you look for this is dabbed beam. This is very critical. Here we are talking in this presentation about very critical elements, heavy loaded elements, same like dabbed beam. Here, if you look that the beam, for example, will be depth 1 meter, but when you come at the edge or at the supporting point, maybe it will be only 50 centi or sometime lesser than this. So you will transfer a huge load from the beam to the supporting edge. So we have to satisfy that this reinforcement is is safe against bearing pressure and bearing stress at this areas. Um, so this is one of the most common example that we have to use, or we can use the curved bar node. Here we have a tie, horizontal tie, here vertical tie. So here we can now we connect them together, so they will work as a one bar, but we have to satisfy the requirements will be presented in this presentation. By the way, this is example for this also. This picture can be found in ACI 31819 in chapter 23. This vertical tie, horizontal tie here, but they are both independent from each other. So we have to satisfy the anchorage requirements independently. But here what we did, we connect the vertical tie with the horizontal tie to be as a curved bar. Let's discuss about this case. If you have a bar and this bar is attached to a tension force T2 and T1, assume that T2 is larger than T1. Okay. If the T2 is larger than T1, here we have radial stresses, bearing, and also we have shear stresses at this area to balance the load and to satisfy the equilibrium. So here we have to satisfy certain length to make this area safe against the bearing and to transfer the loads from certain point to another point safely. This is common or can be found most likely in the beam column joint. If this is the beam and this is the column, here we have a moment and we have to transfer the moment from the beam to the column. So if the force or sorry, if the beam depth is the same column or is equal to the column depth, this will be straightforward, and as we can see here, the force will be transferred as a compression strut, no shear forces theoretically, as we can see. And here we have to satisfy certain diameter of at this curve to make this area safe, and the load will be transferred safely through this node. But if the depth of the beam is more than the depth of the column, here the lever arm will be more. So the force at the starting point of the bar will be different than the end point of the bar. So the radius will be different than the first case. If you look for this table can be found in chapter 25.3.1 or chapter 25 table 25.3.1. This table is very important to satisfy the anchorage requirements for standard hook and for standard hook 90 degree and 180 degree. If you are using ACI code, in ACI code we cannot consider this as a one length. No, if you need to satisfy this standard hook, you have to satisfy the horizontal length LDH. You can find equation in ACI code to find this LDH, and the minimum diameter for the bend, as you can see here, minimum inside bend diameter, and here L extension. So some engineers, what they are doing, they are thinking or they are calculating this total length as a one unit. No, this is not acceptable as per ACI code. You have to calculate each component independently and you have to satisfy all together. If you cannot satisfy this L extension, you can use this 180-degree bend, but also you have one sorry, minimum horizontal length LDH also. So why I am talking about this table here? Because if you open chapter 23, provision 2310 2, this is the same topic what we are talking about today, curved bar node. Here they mentioned that the or the bend diameter or the diameter of the bend for the standard hook or for the 180 degree shall not less than the values calculated from this table. So first of all, we have to calculate this radius using the requirements in chapter 23. Then we have to come to this table to calculate the a minimum diameter of this bend, and we have to select the larger one. So as we can see here that the ACI code try to connect all requirements together. And here mentioned longer extension will not reduce the minimum LDH required by the code. So if the minimum distance here or the minimum LDH or horizontal length is 50 centi, for example, I'm talking, and here L extension 20 centi, so you cannot say that I need to increase this 10 centi and remove from this 10 centi. No, this is not acceptable. Okay, the first condition discussed in ACI code, if you have node attached to two ties, horizontal and vertical tie, and the forces are equal to T1 is equal to T2. At this time, uh, 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 the the bond stresses equal to zero. Here we have only compression stress. We don't have shear stresses as we have discussed before. This diameter or this curve, sorry, this curve should satisfy minimum radius equal to this equation. To multiply the area of steel, maybe this is 6 bars, 7 bars, this depends on your design, multiply by the yield strength, divided by the width into the plan. يعني far away from the plan. For example, this may be the width of this 30 centi, 40 centi. This is depend on your element, and divided by also FC prime, but not less than half bend diameter of table 25.3. This is what we are talking about now. So you have to calculate first from this equation, then you have to compare with the requirement of table 25.3.1. So this is case number one. This is ideal case if the depth of the beam is equal to the depth of the column and the moment transferred equal at the two edges. Second case, also before this, I think we have missed one. Okay, okay, I will follow the same slide. Second case, if I need to use a hairpin reinforcement as shown in this picture, sometime, if you have multiple layers, you cannot, it's not easy to use curve bars for layers together. Again, if we come here for example, if this is one vertical tie and one horizontal tie, we can connect them using the curved bar, same like that. If we have two layers of ties, yes, also we can do the same. But if we have more layers, sometimes it's difficult, and we can, at this time, we can use hairpin, same like that. We have, in fact, hairpin is suitable for CT node, not CTT. This is, we are calling CTT, but this we are calling C and T, we are calling CT or CCT, because here we have compression from the supporting element. So C, and T. So at this time we can use hairpin reinforcement as shown in this picture, by the way. Here we have beam, dabbed beam, and as we can see here, we have tie, and here we have tie. Here what we did, we used U bar, same like that. This is same like that. We are calling this hairpin. Also for this you have minimum radius. So you cannot fix the reinforcement without satisfying the minimum radius. This minimum radius can be calculated using this formula. This WT is the effective depth of the ties. This is what we are calling CCT. And also again, but not less than the half bend diameter of table 25.3. Here we are talking about this 180 degree. So this also can be very effective. In fact, this is good for multiple layers of steel when you have multiple layers. Also, if you have more than one layer, um, as we have discussed before, here you have to satisfy the diameter, inner diameter. And when you would like to use the formula, if the T1 is equal to T2, you can use this formula. ATS is equal to the total amount of the all reinforcement together. For example, if we have here five bars 20 millimeter and here 5 bars 20 millimeter, so the area of steel here will equal to 10 bars 20 millimeter. But when you calculate the RB, or the minimum bend radius, it will be for the inner. You have to satisfy the inner. The same concept here. When you have multiple layers of reinforcement, assume this is column and this is beam, for example. This is the bottom reinforcement, and you would like to satisfy the standard hook. This is, by the way, calculated by strut and tie model. That's why the critical section is from here, not at the face. By the way, this is a long story. We will not discuss this now. But what I would like to say here, the first layer maybe will satisfy the anchorage requirement. The second layer also. The third layer. The inner layer, this is the most critical case, because now we are keeping some gaps between the reinforcement, same like 25 millimeter. So this will be the least available anchorage distance. So we have to be care always to take care for the inner layer of the reinforcement. Here um, in this case, when you have um, different tension along the or before and after the node. Here we have, as we have mentioned before, here we have CTT node, tie, and compression. T1 is not equal to T2, maybe. First of all, we have to make sure that the resultant force, or sorry, the center of the curve should be placed or located within the joint. As you can see, this is the joint. So this is number one. We have to satisfy this. Number two, we have to see the cover, concrete cover. We are talking here about the cover normal to the plan of the bend. Normal to the plan of the bend. This is into page. If the cover is more than 2 diameter bar, this is no issue, no additional requirement. But if the cover is lesser than 2 multiplied by the diameter of the bar, you have to increase the minimum radius calculated by previous formula. This same like that. You have to multiply by additional factor to take in consideration the lesser cover normal to the plan of the bend. And we have mentioned here, always you have to make sure that the center of the curvature must be located within the joint. This is shaded area. Okay, here we have tension T2 not equal to T1. So the ACI code provides different formula to calculate the minimum radius. In fact, the ACI code will give you one formula to calculate the minimum LCB. LCB means the minimum length of this curve, but we can convert this equation to be in term of minimum radius or bend radius. So the same concept. To calculate this minimum radius, you have to find theta c. Theta c, this is the node, and this is the center line of the tie. This is center line of the tie. We can find the theta using these dimensions as shown theta c. Theta c is required to find the resultant compression to balance the tension forces before and after node A. And here we have to know that the formula used to find the minimum radius is different than the formula required to in case of T1 is equal to T2. Here we will take now a quick example. Here we have a corbel. Uh, I only provided this picture for a clarification. Um, what we will do, we will calculate the minimum radius bend, or the diameter or radius of the bend minimum for this curved bar to satisfy the requirements of ACI code. In fact, this is, I think, British units. I converted to metric units only for clarification. Here we have column 16 by 16 inch, 60 KSI yield for the steel, FC prime 5000 BSI, and here we can see the internal forces of the strut and time model of normally ACI code provides two methods to calculate or to design the corbel. One method is simplified with a certain conditions. You have to meet them first. And the second general method can be used for all cases of corbel, strut and tie. This is strut and tie. And these struts and this tie and this also tie. Here we have horizontal tie and vertical tie, and we need to satisfy the anchorage requirement using curved bar node provisions. First of all, here as we can see here, tie BD, we are talking about BD, this tie vertical one. We need to find the area of steel required for this tie. In fact, we have assumed to use four 20 millimeter bars. If we calculate the nominal axial tension can be provided or resisted by this amount of reinforcement, it will be straightforward. 5 multiplied by area of steel by yield strength will give you around 79.2 kib, which is more than 75.8. Okay, now we need to calculate the minimum radius. First of all, we will calculate using CTT node stress. This is the first formula. Now, what we will do, we will use now the radius one time using this formula. If we assume that T1 is equal to T2, for example, and for step number 2, we will calculate using this. By the way, we have to use this. Why? Because already the force here is 46 kip and here is 75 kip. So already they are different. But for comparison purpose, we need to calculate using different equations to see how much the difference between them. If we use the first equation, uh, we will apply straightforward. 2 multiply by total area of steel for 4 bar 20 millimeter. Yield strength given. B is the width of the this element. The width is around 16 inch. Multiply by FC prime. So minimum radius required for this area using this formula is 66 millimeter. By the way, this is not our case. We will not use this, but only for purpose of comparison. Okay, the code told you to calculate one time using this formula and also to check with the standard bend using table 25. If we go for that table, we are talking about this table. Here the diameter is for bar up to 25 millimeter is diameter is 6 dB, which is the radius will be 3 dB. So here, if we go to 3 dB, will give you 56 millimeters. So as we can see, the equation mentioned in chapter 23 for the curved bar node uh, gives higher radius. Okay, if we go for now the second condition, that once the T2 is not equal to T1, To calculate this minimum radius, we have to find the development length. Why? If you look for this equation here, we have development length of the bar. So we need now to calculate the development length. This is straightforward. If you go for ACI code, I will show you quickly. If you go for chapter 25, here, here. We are talking about this equation, but this is in metric, by the way. And here, as you can see, multiplied by 1.3. Why? Because this is for top bar. This is top bar, and the bottom concrete is more than, I think, 300 millimeter. It's already 450 millimeter. So multiply by 1.3. So LD is equal to 825 millimeter or 33 inch. Okay, now we will go for this equation, which is mentioned in the code for different forces. If you go for ACI code, curved bar node, not this. This is we are talking about T. Here different. This LD is required to find LCB, and we said LCB. This is this is the LCB measured along the center line of. This is the minimum length of the curve, but we will convert this LCB to be in term of minimum radius. This will be the same equation, by the way, but only we will change the terms. Here the minimum radius will be how much? 200 millimeter. As you can see, this is very high. Here we have calculated in the first condition 66 millimeter, but this is not our case. Our case is here 200 millimeters. So to satisfy the balance for these forces and to transfer the tension at this node safely without any problem, we have to provide minimum radius 200 millimeter or 8 inch. As you can see, note that required RB is much greater than standard. Standard this. Most of engineers, they are using this. As you can see, this is 56, but in fact, this is not acceptable. Again, we are talking here about the strut anti-model solutions. Okay. Now, if the designer decided to design this element using the simplified method or conventional method or traditional method, but by the way, you have to know that traditional method or approach has some conditions you have to satisfy. Okay, if you are using traditional approach, you have to satisfy the LDH from the face of the column. This will be the LDH, minimum LDH from the face of the column to the node. If you need to calculate this, this is the LDH equation can be found in ACI code. If you will calculate how much you will find, 317 millimeter. So this is the minimum length that can be used to satisfy the anchorage. Sometimes the width of the element is lesser than this, so you cannot use this also. You have to try to use, for example, headed bars. But if you decide to use curved node provisions to satisfy the anchorage at the CTT node, you have to know that for this case, the minimum radius is equal to 200 millimeter. I am sorry for late, in fact, and I hope that I was talking clearly. Always I am preparing my presentation in Arabic and for Arab people, but always my followers, they are requesting me to make the lectures in English. Thank you guys, and I hope this will be very useful for all. Thank you very much again.